When earthquakes and other natural disasters strike, many people die in the initial event. Of those who survive, many still die waiting for rescue crews as they lie trapped beneath rubble and within collapsed buildings. These deaths, while tragic, are preventable. If rescue crews can locate victims faster, they can save more lives before it's too late, thus decreasing the total death toll. Our prompt was to design a solution to this problem by creating an ant inspired search and rescue robot. Our robot needed to be maneuverable in small, uneven spaces, possessing the necessary equipment to effectively locate trapped people. This design challenge initially drew our attention because of its proposed complexity and requirements of a biologically inspired design. Organic design often leads to clever solutions that are often missed with conventional thinking. In the beginning stages of the project, we sought to utilize aspects of previous designs and improve them for better functionality. Many other projects utilized legs. These helped with the robot grounding out on rough ground and getting stuck. Tracks, however, are more reliable. We settled on a track assembly that could pivot to adapt to uneven spaces, like legs, but also had the reliability of conventional tracks. We also came up with the idea of adding a water tank and extendable straw. We thought this addition made sense, as it was something that hadn't been done before, and it would help trap victims to survive longer while waiting for rescue crews.
Unfortunately, this led to space constraints. The water tank and extendable straw took up valuable space needed for other, more important components, like the heat probe system, the camera, speaker, and microphone modules. After talking to our mentor, Jimmy, we realized that the most important factor in search and rescue isn't bringing supplies, but simply locating a victim. We focused on camera and heat probe designs that could achieve versatile motion outside of the robot, but could also collapse inwards into the metal robot shell for protection. Our thinking shifted. A big iteration we worked on was changing our design to incorporate three body segments to allow for more internal space. As we iterated on our design, we came up with a more unique heat probe system that would still use an extendable straw mechanism, but instead of delivering water, it would pass a skinny heat probe through a tight space when the robot could go no further. For lightweight design, we used a compressed air system with an input and output pipe that effortlessly drives the heat probe inwards and outwards. For increased heat probe functionality, this flywheel is attached to a motor that allows the heat probe to reach any position. This design allows the heat probe to remain secure, but also extend significantly and adapt to a small environment just like an ant. Given the prompt of an ant robot, a creative choice we made was to make the robot appear like an ant via the probe mount pinchers at the front and the microphone eyes.
One team member was tasked with designing the segmented frame, which allowed the other two team members to model their components around the dimensions of the frame. This strategy for designing the robot was more successful than the previous iteration. We were able to put our components into assembly and easily fit the components in the right place with a sub-assembly approach. Also, the module-based structure of the robot allows for cheaper and easier manufacturability because the parts can be made out of sheet metal. From what we observed, previous capstone projects mostly involved designs that utilize wheels or legs for maneuverability. One of the most notable ones included a spring-loaded flicking device for getting the robot unstuck. We have a similar method for allowing our robot to get unstuck, which is a pivoting tread mechanism. However, instead of wheels or legs, we decided that treads would perform best in a collapsed building environment due to their grip and durability on unpredictable surfaces. We prioritized practicality and cost in our design, so we pivoted from ideas like the water tank to technological solutions like cameras, speakers, microphones, and a heat probe that would actually find a person. Additionally, our circuit board module contains a GPS. Once a person is found, transmitting the location becomes the most important thing. Overall, we believe that our design offers the best balance of manufacturability, durability, and functionality.